Imagine a carriage designed so perfectly with such exact logical precision that every single piece of wood, metal, and leather ages at the exact same rate.
Right.
It runs flawlessly for exactly 100 years to the day. And then one afternoon, while it's just railing down the street, it doesn't break a wheel or, lose a spring.
Yes.
That simply dissolves, just turns into a pile of dust that goes to pieces all at once. No slow breakdown, no rusty parts, just a perfect, vibrant life and an instant painless end. Isn't that the human dream?
It really is. It's kind of the ultimate optimistic vision for aging. That metaphor actually comes from this 1858 poem by Oliver Wendell Holmes.
Oh, the one Hache, right.
Exactly, the wonderful one Hache. And the reason it resonates so deeply with us is because it represents, well, basically everything human biology is not.
Okay, let's unpack this. Welcome to today's Deep Dive, everyone. We've got a really fascinating stack of source material today, centered around the research and theories in Contro 2 aging.
Yeah, it's a great collection of sources.
And our mission for you on this deep dive is to explore the actual biological mechanics of our own mortality. We're asking the big questions here.
Right.
Like, why do our bodies grow old? Is it just an accumulation of random damage, or is it a pre-programmed countdown?
And of course, the million-dollar question, is there any scientifically viable way to stop it?
Right.
But to even approach those questions, we have to clear up this massive societal misconception right out of the gate. Because we constantly hear that human longevity is skyrocketing, right?
Yeah, you see the headlines all the time.
Exactly. And it creates this illusion that we are slowly conquering aging. But the sources are super clear. We are not. We are simply conquering early death. There is a very rigid distinction between life expectancy and maximum lifespan.
Let's break that down, because I feel like that difference is everything. Life expectancy is really just a statistical average. It's the expected years of life from birth, right?
Right.
And sure, that number has absolutely transformed over the last century. But that transformation isn't because our underlying biology changed.
No, not at all.
It's just because we stopped dying in childhood. I mean, we developed vaccines, antibiotics, clean water systems.
Yeah, the average went up because infant mortality plummeted. We learned how to treat infectious diseases and basically smoothed out the early bumps in the road.
Exactly.
But the maximum lifespan, which is the absolute biological ceiling of how long a human body can theoretically function, that has barely budged since antiquity, that ceiling appears to be hard-capped at around 120 years.
Which is wild. And the verified records bear this out completely, don't they?
They do.
Like, out of the billions of humans who have ever lived, the ultimate outlier is this French woman named Jeanne-Louise Calment. She died in 1997 at the documented age of 122.
And her life was so exceptionally long that she actually saw Vincent van Gogh in person when she was a teenager.
Wait, really? She saw Van Gogh?
Yeah, it's incredible. But she's the anomaly that proves the rule. I mean, nobody else has genuinely breached that 120-year barrier. And it's not just us. This hard cap isn't unique to humans. It seems genetically fixed for every species, even though the actual lengths vary wildly. Like mice hit a brick wall around 3 years.
3 years, yeah.
But then certain tortoises can coast to 177 years, or there's a bristlecone pine tree in California pushing 4,500 years old.
Which totally begs the question, why the massive variance? I know there's this long-standing biological idea in the text called the rate of living concept.
Oh yeah, the whole metabolism thing.
Right. The underlying logic is that metabolism basically dictates lifespan. The faster an organism burns energy, the faster it wears out and dies.
So you picture like a tiny hummingbird with a heart rate of 1,000 beats per minute.
Just burning out in a few years.
Exactly.
Exactly. And you compare that to a giant, slow metabolizing tortoise surviving for a century.
I mean, it makes intuitive sense. You run the engine hot, it breaks down faster.
But the source material points out that humans completely shatter that theory. We expend an enormous amount of energy over our lifespan. Like, our brains alone consume a massive chunk of our daily calories.
Oh, absolutely. Our energy metabolism per body weight is, what, 4 times greater than most other mammals?
Yeah, exactly. And to make it even more puzzling, think about chimpanzees. Our DNA is more than 98% identical to chimps.
Right.
Yet chimps hit their biological ceiling at about 40 years. We live almost 3 times as long, burning significantly more energy, but operating on basically the exact same genetic code. How does that make sense?
Well, that 98% genetic match is actually the detail that keeps longevity researchers awake at night.
Really? Why?
Because if we share almost all our DNA with an animal that ages 3 times faster, it implies that the biological rate of aging is controlled by an incredibly tiny fraction of our genome.
Oh, wow.
Yeah, we are talking about less than 1% of our genetic code being responsible for this massive leap in human lifespan over the last 100,000 years. And if the mechanism controlling aging is that highly localized, it gives scientists hope that it can be, isolated, understood, and potentially manipulated.
That's incredible. So what exactly is that mechanism building the 120-year ceiling? Because the research divides the biological theories of aging into two broad philosophical camps, right? Chance and fate.
Right, exactly. Chance and fate.
Like, are we just taking on water until the ship sinks? Or is there an actual timer in the engine room set to blow? Let's start with chance. These are the wear and tear theories.
Yeah, so the premise of chance theories is that aging is simply the accumulation of random, uncoordinated damage at the cellular level. Take the error catastrophe theory, for example.
Okay.
Every day, your cells are dividing and replicating your DNA.
The text uses a great analogy for this. Think of it like making a photocopy of a highly detailed architectural blueprint.
Oh, I love this analogy.
Right. That first copy looks pretty sharp. But you don't use the original for the next copy. You take that first photocopy, put it back in the machine, and copy it again.
And then you copy the copy.
Exactly. With every pass, microscopic specks of dust, tiny alignment errors, slight fades in the ink, they all just compound.
Fast forward a few decades, and you've copied that blueprint thousands of times. The lines are blurry, the dimensions are completely illegible.
Translated to your biology, those random errors in DNA replication mean your cells start producing malformed proteins and enzymes. The cellular machinery gets gummed up with degraded instructions, and the tissue just stops functioning properly.
Right. And another massive player in the chance category is the free radical theory.
Oh, yeah, free radicals. You hear about those all the time in supplement ads.
Exactly. So as our mitochondria burn oxygen to create energy, they occasionally produce unstable oxygen molecules called free radicals. These molecules are missing an electron, so they violently bounce around the cell.
Just tearing electrons away from cell membranes and mutating DNA.
Right. And this is the exact mechanism that launched the multi-billion-dollar antioxidant industry. Everyone drinking pomegranate juice and taking vitamin E supplements is basically trying to neutralize those free radicals.
Sounds like a solid plan, honestly.
The logic seems sound, yeah, but the actual biology offers a pretty harsh reality check.
Let me guess. It doesn't actually work.
Not really. The body produces its own endogenous antioxidants to handle routine damage. The text notes that dumping external antioxidants into your system via supplements has shown minimal effects on the actual aging process in animal studies.
Wow, minimal effects.
Yeah, because you can't simply flood the body with vitamins and expect them to force their way into the precise microscopic locations inside the mitochondria where the free radical damage is actually occurring. Wear and tear is incredibly localized and stubborn.
Okay, so that is the chance argument.
Yeah.
We're just getting battered by microscopic entropy. But I feel like the fate theories are far more profound. Like, what if aging isn't accidental damage at all? What if it's deeply programmed into our biology?
This is the cellular theory of programmed aging. It's anchored by this landmark discovery in the 1960s by Leonard Hayflick.
The Hayflick limit.
Exactly. He proved that normal human cells do not divide indefinitely. Even when they're placed in a perfect, nutrient-rich laboratory culture, they divide about 50 times. And then abruptly, they stop.
Because there is an actual physical counter inside our cells. We now know that counter is the telomere.
Right.
Telomeres are these tiny repeating segments of DNA at the very ends of our chromosomes. Think of them like the little plastic caps at the ends of your shoelaces that keep them from fraying.
That's a perfect way to visualize it.
Every single time a cell divides, a tiny piece of that telomere cap gets snipped off. When the cap is completely gone, the cell recognizes that dividing again would damage the actual genetic code, so it permanently retires.
What's fascinating here is how truly unsettling and rigid this internal clock is.
What do you mean?
Well, if researchers take cells from an 80-year-old and put them in a dish, they divide significantly fewer times than cells taken from a 20-year-old.
Oh, wow.
And if you freeze a cell after, say, 20 divisions, keep it on ice for years and thaw it out, it doesn't reset. It divides exactly 30 more times and then stops. The cells retain a deep biological memory of their own age.
They know exactly how much time they have left. That is slightly terrifying.
It really is.
And if we can't negotiate with the Hayflick limit, and we can't outrun the cellular photocopying errors we talked about, we have to look at an entirely different strategy.
Right.
What if the goal isn't to extend the 120-year ceiling, but to completely redesign how we experience the years leading up to it?
This brings us right back to the philosophy of the one Hache from the beginning. In gerontology, this is known as the compression of morbidity hypothesis.
Championed by James Fries, according to the text.
Yes, Fries. And morbidity, for those who might not know, refers to the period of sickness, frailty, and loss of independence at the end of life.
So Fries argues that instead of obsessing over pushing our maximum lifespan to 150, public health should focus entirely on squishing all of that physical decline into a tiny window at the very end of life.
Exactly.
So you live with full vitality, playing tennis, living independently until you are 85 or 90. Then, over a span of just a few weeks or months, your system shut down and you pass away.
It relies on creating what they call a rectangular survival curve. In the past, human mortality looked like a diagonal slide. People were constantly dying at every age from predators, plagues, or accidents. Today, medicine has flattened the top of that curve. Most people survive infancy, make it through middle age, and stay alive until the mortality rate drops off a cliff in their 80s.
But the text presents a really terrifying counterpoint to this strategy. Think about what modern medicine actually does. It's mostly putting out fires.
Oh, completely.
We have become incredibly good at stopping people from dying of acute events like a sudden heart attack or a stroke. But if we save someone from a fatal heart attack at age 65, we aren't stopping them from aging.
No, we're just ensuring they live long enough to develop slower, more agonizing conditions.
Right. We might be inadvertently trading rapid mortality for prolonged morbidity. Surviving the heart attack means you live long enough to experience a decade of severe osteoarthritis or macular degeneration or the profound cognitive loss of Alzheimer's disease.
Which means we might not be compressing the suffering at all. We are expanding it. We're expanding the amount of time humans spend in frail, disabled bodies.
And the demographic data actually shows that. As life expectancy has climbed, the sheer number of years people spend living with chronic illness has actually increased in many populations.
It really forces a reckoning with the entire medical model. I mean, fixing individual diseases one at a time is basically like playing whack-a-mole. You cure heart disease, cancer gets you. You cure cancer, dementia gets you.
Which is exactly why an incredibly vocal faction of scientists argue that playing whack-a-mole is a total waste of time.
Right.
They believe we need to stop treating the symptoms of aging and start treating aging itself as a disease, like a disease that can literally be cured.
This represents the great schism in modern longevity research. You have the scientific skeptics on one side versus the advocates of radical life extension on the other.
The optimists are led by figures like Aubrey de Grey, the architect of the SE-SBAT project.
Right. Strategies for engineered negligible senescence.
Exactly.
Yeah.
He completely rejects the idea that a fixed lifespan is a biological law. His approach isn't about slowing down the clock. It's about going into the engine and repairing the damage.
Yeah. SCNS focuses on highly specific biological targets. For instance, clearing out senescent cells.
What are those?
They're basically zombie cells. They've hit the Hayflick limit, stopped dividing, but they refuse to die. Instead, they just sit in our tissues and secrete inflammatory toxins that degrade all the healthy cells around them.
Ugh, zombie cells. That sounds awful.
It is. De Grey argues that if we develop therapies to periodically sweep out these zombie cells, clear out the molecular garbage, and repair mitochondrial mutations, the human body could theoretically maintain itself indefinitely.
He famously claimed the first person to live to 1,000 years old is already walking among us, didn't he?
He did.
I mean, it sounds like pure science fiction. It echoes technologists like Ray Kurzweil, who advocate for surviving just long enough for nanobots to handle our cellular repair.
It does sound out there, but we have to acknowledge that scientists have already achieved radical life extension in the laboratory. They have scientifically proven ways to alter maximum lifespan.
Really? Oh.
Through both genetic manipulation and environmental stress. On the genetic front, evolutionary biologists like Michael Rose have selectively bred fruit flies. He chose only the flies that reproduce at the very end of their life cycles.
Okay.
By forcing evolution to select for late life vitality, he created a strain of fruit flies that live 50 days instead of the normal 25. He literally doubled their absolute maximum lifespan.
Wow. And the text notes that applying that biological math to humans would result in a 240-year lifespan.
Exactly. And the environmental method is even more intense. It's caloric restriction.
Oh, I've heard about this.
Yeah, scientists have known for over half a century that if you severely restrict the calorie intake of certain mammals, cutting their food by 30 to 40% while maintaining basic micronutrients, they live significantly longer.
How does starving them make them live longer?
The mechanism behind it is fascinating. When an organism is starving, it stops prioritizing growth and reproduction. It shifts all its resources into defense and repair. It triggers this process called autophagy, where cells start breaking down and recycling their own damaged proteins just to survive. So by keeping the animal in a perpetual state of mild starvation, its biological house cleaning systems just run constantly. It dramatically slows down age-related deterioration.
So what does this all mean for us? I mean, we can breed immortal fruit flies and starve mice into living 30% longer. But translate caloric restriction to an actual human life.
It's pretty grim.
To trigger that survival mechanism, you would have to restrict yourself to a meager 1,400 calories a day, every single day for decades.
Yeah, it's extreme.
I have to ask you, would you subject yourself to perpetual gnawing hunger and zero physical robustness just to eke out an extra 10 years in your 90s?
Definitely not. The quality of life trade-off is just staggering. And this is exactly where the skeptics enter the chat.
Right, experts like S.J. Olshansky.
Yes. Olshansky aggressively dismantles the claims of Aubrey de Grey and the radical life extension camp. He views the idea of treating aging as a curable disease as a dangerous illusion.
He calls these promises the work of prophets of immortality, right?
Exactly. Selling the same fountain of youth snake oil that humans have fallen for since the dawn of civilization.
The skeptics argue that there is zero evidence in human gerontology to suggest we are anywhere near fundamentally altering the aging process. But beyond just the lack of medical technology, they point to a much deeper structural problem with trying to cure aging.
Yeah. If we connect this to the bigger picture, we have to look at aging not through the lens of medicine, but through the lens of evolution.
This was my favorite part of the source material.
It's brilliant. Leonard Hayflick, the same scientist who discovered the cellular division limit, he uses this amazing analogy. He compares the human body to a cheap watch.
Right. Because the manufacturer of a cheap watch doesn't care if it works for 50 years. They only care that it runs perfectly until the warranty expires.
Exactly. Evolution operates with that exact same brutal pragmatism. Natural selection only cares about one outcome, the survival of the species.
It only funds the cellular repair mechanisms long enough for you to reach sexual maturity, reproduce, and keep yourself alive until your offspring are independent.
Historically, for humans, that means hitting your mid-30s or early 40s. Once your kids can survive without you, the biological warranty is essentially up.
That is so bleak, but it makes so much sense.
Right. Building a biological self-destruct sequence to kill off an organism immediately after reproduction requires a massive expenditure of energy. And evolution is lazy. It doesn't bother.
So instead, it just pulls the funding from the repair departments.
Precisely. We are endowed with excess physiological capacity like dense bones, a robust immune system, just to ensure we survive the reproductive gauntlet.
And once we pass that threshold, we're basically just coasting on those reserves.
Yep. The telomeres shorten, the DNA copying errors pile up, the zombie cells accumulate, we slowly break down, completely abandoned by natural selection, just ticking away and losing time long after the guarantee period has ended.
So we aren't a broken machine waiting to be fixed by medicine. We are a machine that is operating exactly as designed.
It's a huge paradigm shift. Fighting aging isn't fighting a disease, it is fighting the entire architecture of natural selection.
Wow. It really forces you to evaluate what you are actually optimizing for in your own life.
Oh, completely.
Are you structuring your life around chasing maximum longevity, enduring constant restriction in the hope that SENS technology arrives in time to repair your cellular damage? Or are you optimizing for the compression of morbidity?
Accepting the 120-year ceiling, or even the 85-year reality, and focusing entirely on maintaining vitality and independence for as long as possible.
It's the classic divide between adding years to your life versus adding life to your years. We've journeyed from the romantic perfection of the one-hoss shay down into the gritty reality of DNA degradation and telomere clocks.
We really have.
We've seen how curing acute diseases might just trap us in chronic decline, and we've explored the battle lines between those who want to accept our evolutionary warranty and those who want to completely rewrite the code.
But as you think about your own place in that debate, There is one final, rather chilling biological reality to consider from the research.
Oh, yes, this is wild.
We spent this entire time talking about the Hayflick limit and how normal human cells must eventually stop dividing to protect the organism, right?
Right.
But there is one famous exception.
The HeLa cells.
Yeah. In 1951, scientists took a tissue sample from a woman named Henrietta Lacks. Those cells, known as HeLa cells, have been growing in laboratories around the world for over 70 years.
They achieve true biological immortality.
They never hit the Hayflick limit. Their telomeres constantly rebuild themselves. They divide endlessly, defying the aging process completely.
But HeLa cells are cervical cancer cells.
Exactly. They are the definition of uncontrolled, infinite replication.
Which leaves us with a profound realization. The only human cells that have successfully defeated aging, bypassed the evolutionary warranty, and achieved true biological immortality are cancer.
Right. So as we pour billions of dollars into the desperate human pursuit to live forever, we have to ask ourselves, is an immortal biological machine a medical miracle, or is it simply a mutation that destroys the host?
Something to think about. Until next time, keep digging deeper.